Thank you. So we'll start it off with the segue into accents. I'm half Australian and half Southern, so I'll probably speak fast and have the mush mouth thing we talked about earlier, so try to avoid that. So I'm based in Salt Lake City at the Remote Sensing Application Center, and just to give you a little piece on our mission is we're a detached Washington office for the Forest Service based in Interior West, and we collaborate with a lot of different regions across the whole country in Alaska, work on remote sensing projects and try to use remote sensing technology to help people deal with their natural resource objectives. And so some of you probably, maybe all of you have heard of Lidar. Some of you might not know exactly what it is. So we'll talk just a little bit about and build the base there before we get into the mapping part of it. And sort of some of the considerations for using it for vegetation modeling or monitoring. It's a little different than a lot of the uses of Lidar. And then we'll talk about the specifics of modeling biomass and other forest inventory variables using Lidar technology. So Lidar essentially is one tool we can use to measure or monitor our natural resources. And generally in the Forest Service and most natural resource management agencies, we have a few things we need to know about a resource to manage it well. And one thing is inventory. How much of it is out there, which is really pertinent to this conference? How much biomass is there? And maybe it can focus your efforts in harvesting it for energy and other topics that you've heard about today. So how much of it? Where is it? In some cases, the species is important. What species is it? And has it changed over time? And so when we use Lidar technology to address these issues, we're really successful in telling how much is out there and where that amount is. We're not as successful with Lidar, per se, as telling what tree species it is. Is it Doug fir or white fir or subalpine fir? We can't do that with Lidar. We need other information to do that. And has it changed over time? Potentially we can do that, but since Lidar is a relatively new technology, we don't have the reoccurring data sets or the temporal resolution to be able to do that. So hopefully in the future, as Lidar is continuously collected more and more, we'll have that capability. So just the real basics here, Lidar is just basically a laser that's flown on a fixed wing airplane. The acronym stands for Light Detection and Ranging. And so what happens is the airplane, fixed wing airplane, flies over, sends out a bunch of laser pulses. They hit targets on the ground and they reflect back. So we can use basic physics and figure out where those pulses of light touched a target on the ground and came back. We can measure the distance and the angle, and we come up with these georeference points in space. So it's like a 3D point cloud, if you will. And we can collect massive amounts of these laser pulses every second. So we can get these really, really detailed, large data sets, which are great, but it also can be problematic when we're talking about processing them. So just sort of talk about this graphically. We fly over, we send a pulse of light, like a beam of light that comes out of a flashlight. If you point it on the wall, you see a circular beam. And then what we do is we send those out. They're near-infrared light. And this single pulse of light strikes maybe potentially different features on the ground. Maybe it hits the top of the tree, the mid-canopy, and then the ground surface below. And when we dissect the pulse, we get what we refer to as returns. And when we dissect the pulse and those returns graphically, we can see each one of those pieces from the pulse of light we can separate out as its own data point. So what does this do for us? So when we fly over, this is an aerial photograph of an area. We see different targets here. We see trees, we see structures, we see roads, and we can fly the Lidar sensor over this area. We collect all the information from the pulses, and what do we get back? We get a 3D point cloud. And this point cloud is colored by height, so the cool colors represent the lower elevations, if you will, and the warm colors up. So we can see the ground surface below in blue. We see structures. We see trees. So we're getting a full 3D sort of representation, and then we start to try to extract information. And in this scenario, we can subtract a ground surface underneath. And so being able to see the trees and the ground surface underneath is really important because that allows us to normalize all the information to height above ground. And that allows us to start talking about how tall the trees are and how dense they are, and then we can, from there, move on to talking about biomass. So this is just sort of a quick overview of sort of, basically anything you can see from above, you can see with Lidar. And you get a 3D sort of picture of it. Power lines, the ground surface, structures, roads, a lot of hydrology applications. But what we're going to talk about today is vegetation. So we can also talk about generally the products that you're going to start with. They fly Lidar acquisition, let's say on your forest. It's 100,000 acres, 500,000 acres. You're going to get a suite of products. You're going to get the bare earth surface, so the topography to a scale of less than 1 meter potentially. You're going to get a highest hit surface, and you're going to get this raw point cloud. So that's the 3D visualization point cloud that you get from the vendor. When we talking about vegetation, there's a few things that Lidar directly measures. And it measures the height of the canopy. It also measures essentially a percent canopy cover or a density of the vegetation. So those things aren't modeled. They're actually sampled with the technology. And we use that to help us model biomass. And then in this last sort of scenario is we take the data we extract and we create models that estimate biomass across the landscape. Okay, so let's look at a vegetation point cloud in a little more detail. And we just sort of have a very forested scenario here with various densities and canopy covers. And we can go in here and start to look a little more closely. And we can see that the vegetation structure is being recorded or sampled from the technology. We can also see if we look at a cross-section, we're seeing the difference in topography, the height, the density. And then we can compare stands, and we can actually start to see mid-story density differences. So not only are we just the top and the ground, we're seeing densities inside the canopy. There's a lot of areas where biomass in that mid-story, if it's too dense, is detrimental to wildlife habitat, or it offers potential for devastational fires. So being able to figure out where that is on large areas is really valuable, and we really couldn't do that with a lot of remote sensing technology before. So what we're talking about now is we're going to talk about modeling biomass from this information we've gotten from the point clouds. To do this, we need field data. So we can fly over the landscape. We can tell how tall the trees are. We can tell how dense they are. But if we really want to get some kilograms per hectare of biomass, we need to go out into the field and measure that on plots. So we do need field data for this technique. We also need to extract the appropriate information from the Lidar data. And to do that, we clip out corresponding plots to our field plots, same diameter. We clip out that little piece and we characterize it in a lot of detail and compare that to our field measurements. Then we also take that size of the plot, let's say it's a 30-meter diameter plot, fixed plot on the landscape. Then we'll divide our whole project area into 30-meter pixels. And then we can calculate this exact same statistics for every 30-meter pixel on your 200,000 acres. The same statistics you had for your, let's say, 100 field plots if you're lucky. And then here's the fun part. We got to try to build a relationship between what we measure on the ground and what the Lidar sees. Is there a relationship, and can we push it across the landscape? And then after we create these fancy models, we apply them, and then we take them to the people who understand the landscape and say, are these ridiculous, or are they good? Do they make sense? So that's a really crucial step that we have to remember. These are models. Here we go. So I'm going to focus on one area that we perform this technique. It's in southeastern Arizona, just above Tucson. It's a pretty unique area. It's a sky island ecosystem. So it's surrounded by desert. It rises up in a lot of elevation, and they have subalpine fir. And these sort of alpine conditions. They're very isolated. They're very sensitive. This one's been burned quite devastatingly. There's a lot of insect damage. There's some endangered species there, so they're very interested in it. Not necessarily to harvest the biomass for energy, but to know what's out there so they can manage it and stop these devastational fires or insect outbreaks. So 80 field plots were collected across 85,000 acres. Now the colored image there is our canopy height model, colored warm to or cold to warm again. So you can see that all the tall vegetation is sort of in the center in the upper elevations. And that's where they really wanted to focus the study. They were fixed plots. They were about a 1/10 acre in size. Now, one key point to remember for this methodology is that we really need really accurate plot locations. Lidar data is super accurate. You can get accuracies sub-meter, sub-10 centimeter across a wide swath of landscape. So if you go out there and collect field data and you use a handheld GPS and you're within 10 meters, then you're looking at the wrong trees when you build your relationships. So you need like a resource/survey grade, tripod GPS, dual phase, corrected, all that stuff. You want to be really careful with your locations. And you can probably relate to this. We don't want to just look at the large commercial species. We want to measure all the biomass because LiDAR samples all of the biomass. It's not just looking at the commercial timber. And when we go out there to sample or create our field plots, we want to try and sample the variation across the landscape. So we're trying to build a model between the LiDAR data and all conditions on the landscape. So stratified random is probably ideal. And using some of the LiDAR data to tell you where to put the plots is a really good idea. So you cover the variation on the landscape so your models aren't extrapolating off the ends in areas that you're interested in. These are all the parameters that we set out to try and model across the landscape. Biomass at the top, some timber inventory variables, basal area, volume, SDI, and then we also had some fuel parameters at the bottom there. So these are all the things we were interested in modeling and attempted to model with this technique. So as I mentioned before, not only do we measure field plots and calculate those inventory parameters, biomass, volume, we also clip out the exact same area in the LiDAR data, and we calculate a bunch of statistics, sort of all sorts of density and height statistics about that individual plot. Then we're going to try and relate that to what we see in our field plot. So here's sort of a quick example. We sort of find our best predictors from the LiDAR. And so let's focus on biomass at the top. We see we have two predictors that help us build this equation. We have a mean height from each plot in the LiDAR data. So that makes sense. The average height of the vegetation contributes to more biomass if it's lower or higher. Then that P2 is a ratio, and it kind of represents a density of vegetation. So you think, okay, height and density, that makes sense. They predict biomass. So those are our two predictor values, and you can see there in the nonlinear R squared, we're about 0.87, which is pretty good. So biomass actually came out as the easiest one for us to model. And then you see basal area came out pretty good. Then you look down at the bottom, trees per hectare. For this methodology, that we weren't very successful. We R squared of like 0.2. So different parameters are sampled differently by LiDAR technology, and some of them make sense to model and some of them don't. Okay, so we calculated all those statistics, and we identified that mean height and that density ratio help us build that relationship and predict biomass. Now we take those exact same statistics and we calculate them across the whole project area in a cell size that's potentially or almost the same size as our plot size. And so now we have the relationship. Now we have the exact same metrics across our whole landscape. Now we can apply that relationship across the landscape. That's what's so great about LiDAR technology is it samples every tree in your whole project area, every density, every height. So then we take the equation that we built from the plots and we just take these grids in our GIS and we plug them into that equation. And we just do math with these images. And what we do in the end here is get a biomass map across our whole project area. So sort of in context of this conference, if you want to know where more biomass is and sort of if you want to harvest it for energy, then you can see this map and say, hey, well, we see there's a lot of biomass here. Maybe we should focus our efforts here first. Or you can combine this with the topography and see what makes sense, what's feasible to go in there and harvest or something like that. So that's kind of how it relates, I guess, to maybe some talks from this morning. But again, it's a model. We need to mask it and validate it. We built this model based on forest plots, and we didn't sample anything in, let's say, the PJ or anything like that. So we need to make sure we create a forest mask and get rid of all the areas in our project area that don't meet our forest criteria. So that's something we need to do. So once we do that, this is sort of a full list of all the outputs we created, the equations we created, and then we applied across the landscape. Some of those equations are pretty messy, polynomials, and there's all sorts of different ways to do regression modeling, and some of you probably know more about it and can argue it better than me, and I'm not going to. But as I mentioned, this masking scenario, because these are forestry-based plots, they're not grass, they're not scrub, desert. You know, we didn't do field plots there, so our models won't work there. So we need to mask those areas out. So what we did is we just created a forest mask. We can do this really easy because we have the Lidar data. So we can say if something's not more than 3 meters tall and has a certain % canopy cover, it's not forest. So we throw it out. So everything in blue is included, in the little gap areas were excluded from our models. We also had some model extrapolation. So these are areas when we went out there and did our field plots, and then we clipped the same Lidar data out from those field plots. The parameters we used from the Lidar data that correlate to the field plots are in a certain range. But then when we apply those equations we build across the whole landscape, we might go outside of that range. And that's where we don't have confidence that the models are predicting right, because things aren't always linear, as we know. But what we did find is we basically had less than 1% of the pixels that we were extrapolating. So we're pretty happy with that. So we weren't too worried about our extrapolation issues. But this just sort of reemphasizes the point that when you collect your field data for this methodology, you really want to try and cover the variation in the landscape as efficiently as you can. Okay, so these are kind of the final GIS outputs for the landscape. It's about 85,000 acres. So you can see in the upper left are total basal area, live basal area. We're missing biomass. Did we skip one? Oh, there we go. So biomass in the upper left-hand corner at kilograms per hectare across the landscape. So this is a really useful GIS output. Before Lidar technology, we're estimating this with optical remote sensing and field plots. One thing we didn't do in this study is look at species. We used one biomass equation for all species. We can't get species information from Lidar technology, so if you have a good species map to start off with, and you have enough money to collect enough plots in each strata of species, then you could, again, create different models for different species. But, field plots are expensive. We never have enough to model accurately. So we just, generally this technique has been used really well in like Sweden and Scandinavia. They have like 4 tree species, and they have millions of acres. So it works well there. It works really reasonably well here too. We haven't done as much of it in the eastern, southeast and eastern woodland forest because things differ a lot as far as their canopy structures and things like that. So, but anyway, quite successful with an R-squared of 0.88. We can do canopy fuel parameters. We can look at also we go basal area, volume. We did total volume and dead volume too, and we also did total basal area and live basal area. So I was thinking initially this, I wasn't very confident. Structure is structure, heights and mean heights, and you do see some differences with dead trees versus live trees, with the needles and the canopy cover that's measured with Lidar or sampled with Lidar. So I was a little suspicious about some of these. But there's this interesting piece here. This is a world view image, optical image, 1 meter resolution, I believe, maybe 2. It's displayed in color infrared. So the red shows very healthy, photosynthetically active vegetation, and sort of the darker areas and the white areas are sort of bare ground, and then the sort of dark areas are dead vegetation. And which was quite interesting is let's look at the live basal area model. So what I've done is scale live basal area to total basal area. The same. And so now we can see in that burn scar area there's a lot of this lower live basal area reading here, very, very low in the gray, across that burn scar that we saw. But then when we look at, so again you can see that open area where the gray was. But then when we look at total basal area, including the dead trees, we actually see quite an increase in that, which makes sense. So that was really encouraging. And I don't know if that would apply that way across the whole landscape, but I thought that I was very doubtful that we would see difference there. But this logically makes sense, at least in this area, that we were mapping that correctly, at least the trends of it. Okay, so a few things to remember about this. I mentioned this earlier. Your field plot locations have to be extremely accurate. FIA data is great, but it's not always accurate as far as location for this purpose. So you can't just grab FI8 plots and get some LiDAR data and off you go. You have to spend money on field plots, or at least go out and get the location accuracy within sub-meter is really what we want. Good sampling design will limit your extrapolation points. So cover the range of heights and densities across your landscape so that when you build these models, you're not extrapolating off the ends and not really confident in what's going on with them. And regression modeling is hard. It's a complex art even. So have someone who has some idea, or have someone that you can task with that. And then validate the models with local expertise. Again, they're not reality. Okay, so this project was a really good example for me of great collaboration. We had the University of Arizona, Forest Health, RSAC, the regional office, the local forest. So it was a great collaboration of a lot of people. Also the Pacific Northwest Research Station in Oregon. They're leading the way essentially, or at least the Pacific Northwest has done a lot of LiDAR work in estimating these sorts of things, and all the other analysts at RSAC. So that's it.
Questions? I know you mentioned how to try to get to some of that information by field plots is expensive, but can you talk a little bit about the economics of LiDAR?
Sure. So LiDAR is pretty expensive. For this acquisition, it was about 85,000 acres. I believe it was $110,000 to fly the LiDAR. Now it's about $1 an acre for a reasonable size acquisition. So it's getting a little cheaper. The field plots, we got 80 field plots. I think that was about $50,000 for the field plots. We did have some university graduate students lead some field crews, so that was sort of their contribution. And then we also had the local district field crew collect field plots. So, you know, all in all, we're looking at $150,000 for this project before the modeling and that sort of thing. So there's a lot of, for this technique, a lot of data modeling, data management. The LiDAR data for 85,000 acres was about 95 gigabytes. Here you go, off you go. So there's a lot of expense also in the processing part. So, but it's getting cheaper, and these techniques are more established. So. Sure.
Have you had any luck combining LiDAR with hyperspectral to distinguish between the species?
Yeah, I mean, I think if you got the hyperspectral, and maybe you can use some of the heights or densities if you want to do some sort of segmentation or classification that way. So far, I haven't seen too much fusion. I think maybe doing your species first with hyperspectral or even multispectral, and then deciding, okay, do we want to put the structure in there? But yeah, there's a lot of potential for fusing the structural stuff with the optical and getting everything that much more accurate. But I personally haven't done too much.
Any more questions?
Are you finding any of the agencies using this as far as fire effects monitoring, as far as prescribed fire fuel reduction?
There's a lot of fire fuels modeling. I don't think they've really used it fire fuels modeling yet. But for monitoring purposes, we really haven't had those, repeat flights and acquisitions. So eventually, I see maybe LiDAR collection going to some sort of like a NAPE program where the USGS and maybe a couple agencies will fund, or the USDA funds some sort of continuous national acquisition scenario, and then I think it'll be really powerful for that. Now it's sort of a moment in time, and the joke is for this project that any minute it's going to all burn, and so all of these models will be like totally invalid, and because they're it's so volatile down there.
See an extreme use for this for a pre-post 5-year, 10-year type of database collection as far as monitoring fuel conditions.
Definitely, and I think there's I think Susan Hummel in California is kind of looking into that. So we're in collaboration with a forestry ecologist trying to kind of go down that road, but I haven't seen anything that's done that yet. Good question.
Okay.
Thank you.
Yeah.